Hi, this is John Morris from Seagate. The pace of innovation in the global data sphere has never been greater. With agility and flexibility as key enablers for innovation, it's no surprise to see RISC V as a powerful tool to accelerate innovation in data storage. I'm pleased to share our RISC V journey over the past 5 years. Let's first talk about the scale of data growth. New use cases that are data intensive are driving data creation. Immersive experiences like AR/VR, surveillance, autonomous vehicles and machines, and IoT all create data. Machine-to-machine and software-to-software communication will be large drivers for data generation in the coming years. Life-critical data is also expanding. More research in the human cell and genomics, higher resolution imaging and detection capabilities to create faster diagnosis, and more exploration of imaging with neural networks. The CAGR for this data creation is nearly 30%. But each year, only a low single-digit % of the newly created data is stored. In 2020, IDC estimates a total installed storage base of 7 zettabytes, split across hard disk, flash, tape, and optical, with a CAGR of about 18%. But only about 1 zettabyte of new storage will be added in 2020. Or in other words, only about 3% of the newly created data can be stored without deleting something. Much of the challenge for all of us in the storage industry is to find new economical ways to store more. Here is an adaptation of a framework created by Peter Levine describing 4 platforms of computing and the advent of edge computing. Over the past 60 years, we've seen 3 and are moving into a 4th computing platform. In IT1, infrastructure started with the mainframe, a centralized computing model, and this was the beginning of the modern computer era. IT2 brought in the era of client-server, distributed, and decentralized architecture. IT3 encompasses the centralized cloud and distributed mobility infrastructure, and IT4 is the rise of the edge, with the decentralized infrastructure of endpoints and edge that connect to a centralized cloud. We are beginning to see data shift to the edge of the network. A big theme in this shift is sense, infer, and act, as highlighted by Peter Levine in his original talk on these platforms. This shift is what we refer to as the rise of the edge, or IT 4.0. The edge era is expected to capture trillions of connections as machine-to-machine becomes the norm. The edge is nascent and exciting. But what are the implications for infrastructure? What does it mean for storage? To solve for the challenges of IT4 and beyond will require significant innovation, identifying pain points and generating solutions that will allow the world to protect, move, and store the expanding data sphere. Some examples of these pain points and innovations are security. Security is already a central pillar to data sphere innovation, and its importance is growing every day. With the proliferation of multi-tenancy for cost optimization and the massive growth in the number of endpoint devices and sensors, vulnerabilities to data manipulation attacks will explode. Building from self-encrypted devices, we need to explore technology that provides product trust and enhanced data privacy. RISC V's open architecture will play a key role in enabling this ecosystem to provide the data trustworthiness required to secure future data growth. The growth of large data sets that will fuel AI and machine learning workloads presents a significant data movement challenge, causing network congestion as well as concerns associated with cost and power. Innovation in composable architectures and computational storage will allow the optimization of system resources, enabling distributed compute to reduce the need for mass data movement. RISC V's capabilities are expected to play a significant future in addressing these challenges. As the world moves to a hybrid cloud model, data will be provisioned, orchestrated, and stored across a variety of platforms. This data movement will be seamless, automated, and optimized for the required quality of service using containers and CSI drivers. RISC V will play a major role enabling IoT at the far edge, constantly feeding these systems with trusted information. Innovation in data visualization and autonomy will further enable the ecosystem to scale. talk about a few domain-specific examples in hard disk drives. First, we'll talk about real-time processing. Hard drive innovation is continuing at a significant pace, pushing areal densities to address the growing need for mass capacity storage. Seagate is on a path to produce 50 terabyte devices and beyond, and this presents a significant challenge to the positioning technology used to access this capacity. At 50 terabytes, the read-write transducer will need to be able to move across the disk at 2.5 meters per second, while also being positioned with a radial tolerance of 2.4 nanometers and controlling head media vertical spacing within angstrom. This challenge is made more significant given the need to accommodate often uncontrolled external mechanical and acoustic disturbances. To meet this challenge, innovation is required in both the mechanical design of multi-stage actuators as well as servo technology, enabled by real-time processors. These servo algorithms are increasingly complex, built on years of precision motion-controlled expertise and pushing the limits of adaptive and predictive control. This computation needs to occur within tightly coupled timing requirements and within significant constraints of power, space, and cost. On the left, you can see an SoC containing Seagate's first RISC V Core, specifically designed by Seagate for high-performance real-time processing. Building on core RISC V technology, this processor is powering Seagate's RISC V enabled hard disk drive demonstration. More information on this processor can be found in the breakout session, Fueling the Data Sphere by Seagate's Richard Bowen. Through expertise in microarchitecture optimization and targeted focus on instruction-specific latency reduction, the performance of critical servo algorithms has been significantly enhanced by this novel processor. As an example, we've seen a 3x reduction in the cycles required to perform key disturbance detection computation. The efficient performance enabled by this technology will directly enable the future deployment of Seagate's mass capacity solution. Now let's talk about a second use case. With the coming explosion of data driven by sensors, IoT, and endpoint devices, there will be an increasing reliance on autonomous decision-making systems. These systems will bring with them new vulnerabilities where data manipulation from malicious actors can exploit security weaknesses to compromise the decision-making models. To combat these threats, will require innovation and solutions that enable data security. It is key that we trust all data created by endpoints and have ways to validate the integrity and provenance of that data. Data end-to-end integrity and trust requires a data security framework that manages cryptographically protected objects and provides data provenance via domain credentials for proof of origin. Endpoints create data flowing from the edge to the cloud, touched by many intermediaries, all storing and processing data. For any data created by a known and secure endpoint, one can use the security infrastructure of the endpoint to cryptographically secure all data flowing off that endpoint. Optionally, any data created by trusted endpoints can be notarized and then validated for integrity when consumed by other entities. Seagate is investigating how RISC V-based security functionality supports an end-to-end data integrity and trust framework. We've created a prototype of a trusted endpoint using an FPGA development board on which all security-sensitive services are bounded by open-source Keystone Enclave. Based on learnings from that prototype, we decided to dive deeper into trusted hardware using open technologies such as OpenTitan, the first silicon-based open-source root project for root of trust. Seagate is a member and supporter of OpenTitan, and we recognize the potential for open root of trust design to significantly improve the security of future data storage infrastructures. More information on this project can be found in the breakout session, Data Trustworthiness of the Edge by Seagate's Manuel Offenberg. That brings us to Seagate's first RISC V area optimized core, specifically designed to power auxiliary workloads and enable the deployment of security features at the endpoint and edge. It's a 5-stage in-order pipeline core with full physical memory protection, plus enhanced PMP support for strong process isolation. Seagate has designed in several security-relevant features, such as constant time execution. This core provides a great baseline for a security-optimized RISC V solution in endpoints and edge deployment. Additionally, with a highly configurable microarchitecture and feature set, this core can offload domain-specific tasks from general-purpose processors at low cost, low power, and with a small footprint. RISC V and its ecosystem provides a unique foundation from which we will build more secure systems that will protect all data throughout its lifecycle. So in summary, Seagate began its work with RISC V in 2015 with the design of a high-performance microprocessor to solve the domain-specific challenges around real-time processing. Since then, Seagate has become an active participant in the community, contributing to spec development and generating expertise in FPGA prototyping, performance benchmarking, and secure enclave technology. In 2019, Seagate started development of an area-optimized core. This core will solve many application-specific challenges, including endpoint security. This year, Seagate took delivery of physical silicon and has demonstrated a functional hard disk drive prototype powered by this high-performance core. Seagate is fully committed to the RISC V architecture and is looking towards many future applications for this technology, including computational storage and open, domain-specific applications. We look forward to partnering with the wider community to grow this capability and enable an open hardware ecosystem that can help solve the data challenges of tomorrow. Thank you. For more information, be sure to visit our breakout sessions and virtual booth.